Okay, Chapter 6, Section 1, an introduction to enzymes. Now, enzymes, we have recognized their existence back since the late 1800s. A researcher by the name of Edward Buchner, probably pronouncing that wrong, but demonstrated that, via yeast extracts. Remember, extracts, just like life, you've chemically have burst open the cells, but you haven't done it in such a way that you're denaturing the proteins. You're just interrupting the plasma membrane, the cytoplasmic membrane, and you're releasing intracellular contents. Well, you took those intracellular contents and in the presence of sugar showed that there was still fermentation. So it wasn't the actual cell itself fermenting, it was something within the cell. Decades later, now we come to know that what he was looking at, what Buchner was looking at, are what we refer to as enzymes. The enzymes remained intact even though they were now cell-free and were able to break down the sugars, doing it in a, anaerobic state, so you ended up with alcohol fermentation. Most enzymes are going to be proteins, okay? Are there enzymes that aren't proteins? Yeah, we refer to those as ribosomes or ribozymes, and that's for a completely different chapter when we look at RNA and nucleic acids and how those can do work also. But the majority of what we refer to, think of as enzymes in your cell, are going to be proteins. These are proteins that have some form of a catalytic activity. You'll hear me in lectures. I'll always sit there and say enzymes. They cut, they paste, they twist, they tweak. They do one of those and only one of those things. The molecular weight, well, since an individual enzyme's too small to really go through and weigh it out, we have come up with a relative scale based on, the average size of an amino acid. So we call these, we refer to this as kilodalton, or you'll see it just molecular weight, MW. It's not the same as if you're doing the molecular weight of carbon or the molecular weight of oxygen. We go through and based on the size, the number of protons, blah, 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 think it's, this. So this molecular weight, 12,000 to 1,000,000 kilodaltons. We also find that enzymes sometimes need a little helper. Whether that little helper is going to be in the form of, a metal, iron, magnesium, forget, drawing a blank on what Mn is right now, or zinc. What these do is they act as the ion at the center of some much larger organic molecule. Think past chapter, we were looking at hemoglobin, myoglobin. The porphyrin ring itself doesn't do anything without that iron at the center of it interacting with gaseous oxygen. So that iron is acting as a cofactor. That metal is needed there at the center of, or somehow associated with, the protein or the polypeptide, so that that protein polypeptide can have a function. In other times, you're going to see that it's the coenzyme is required. This is going to be a complex organic or metal organic molecule. Could be, a large protein may need a small polypeptide associated with it. That small polypeptide could act as a motif, an attachment to it that allows the coenzyme to function. Or that coenzyme could be the base that other polypeptides are attached to. And thus you get your complete protein. When it comes to the inorganic molecules, copper, iron, potassium, magnesium, molybdenum, manganese, nickel, zinc. These are just some of them. You also have silver. You also have gold in you that are also required for other things. And if you look at table 6.2 in the chapter, you'll notice that there are certain coenzymes, biocytin, coenzyme A, lipoate, nicotine amide, adenine dinucleotide, NAD, remember this from glycolysis, citric acid cycle, tetrahydrofolate, or their precursor, vitamin B7, B5, B12, B2, B3, B6. These vitamins that you have to take in your diet act as the precursor so that, say vitamin B5. Vitamin B5 is going to be the precursor, the base, that other things will be added, attached to, tweaked, cut off of, so that it becomes coenzyme A. Coenzyme A is required for certain metabolic functions. First step of getting the 2 carbons that are, left after pyruvate is transported into the mitochondria. Remember that acetyl group? Well, boom, coenzyme A, based on vitamin B5. Now, how these groups are added, whether the coenzyme A or the inorganic compound is attached, is a base molecule, or just has to be in the presence of, well, that tells you whether it's a prosthetic group, a holoenzyme, or an apoenzyme. Prosthetic group, tightly or covalently bound. It has to be there. You get the prosthetic group and attach it to its protein. You now have what is called the holoenzyme. By itself, you have an enzyme that may or may not be able to function. If it can function, it's very slow, very clunky. When it gets its prosthetic group, its coenzyme or its metal ion put in place, now it functions. Now it's highly efficient. Now it is referred to as a holoenzyme. The base enzyme without the coenzyme, without the metal ion, that's what's referred to as the apoprotein or apoprotein. Tomato, tomato. Coenzyme, metal ion, added to the apoprotein, you get the holoenzyme. A plus B gives you C. All right. Now, to sit there and say enzyme, it's too much. So we like to divide that out, parse that out, group like with like. Rule of thumb. Any word that ends in A's, A-S-E, is an enzyme. Whatever prefaces A's tells you what that enzyme does. So, if you have oxidoreductase, transferase, hydrolase, lyase, it's an enzyme. What prefaces it tells you what it does. So, look at isomerase, ends in A, so it's an enzyme. Isomer prefaces A's. So it's an enzyme that makes isomers. Remember isomers. 2 organic compounds that are going to have the same molecular formula, C6H12O6, but they're going to have different structures. That's what an isomer is. That's what an isomerase does.